So, in the last lecture we had stopped at the hologram of an arbitrary object, okay, which is here. So, we had taken an arbitrary any kind of object and seen what kind of a recording it should be. Now, let me spend a little bit more time on the kind of holographic plate that we are talking about. So, one thing you can understand, see, because we are recording the phase, as I have said before, your holographic plate has to be a hard plate. Okay? It is not a film which keeps moving. Okay? So, you can see that, so that the phase is recorded very accurately. So, what is the quality of the holographic recording plate? Okay. So, we must know a little bit about that. So, you just recollect, I have just put in the intensity pattern there once again. I x is half of E star E, whichever is the final E, which is the addition of reference and the signal. So, it turns out to be E1 square plus E0 square plus 2 E0 E1 e to the power I k x sin theta. I have speaking in terms of the plane wave only, I have not taken a spherical wave. Okay. The fine details of the intensity distribution are recorded on the holographic plate. The condition for maximum on the plate, okay, maximum means maximum of that interference pattern, you know that. When will that be maximum? When this part becomes 1, e to the power I k x sin theta becomes 1. When this is 1, this becomes the maximum amplitude or maximum intensity you will get. Okay. So, the condition for maximum intensity e to the power I k x sin theta equal to 1. Okay. If I write e to the power I theta is cos this plus this, which is just a mathematical e to the power I theta is equal to cos theta plus I sin theta. Okay. So, here I have cos of k x sin theta plus I sin k x sin theta should be equal to 1. Now, there is no imaginary part for this one. So, cos of k x sin theta, this part should be, this part can be 0. There is no imaginary part here. So, I can put this at 0. So, I am just left with this term, cos k x sin theta is equal to 1. If the separation between the maxima is equal to delta x, then I can put k delta x sin theta is equal to 2 pi. Here what I have done is, instead of k x, I have put k delta x. K delta x sin theta should follow this principle of 2 pi. Okay. Then only cos of this whole term will be equal to 1. Okay. And k you know is 2 pi by lambda. 2 pi by lambda delta x sin theta is equal to 2 pi. So, delta x is equal to lambda by sin theta. All right. Now, consider the case where theta, this is just as an example. So, I know what is this delta x, the separation between the maxima is delta x. So, there are two maximas or shown like this. So, separation between them is delta x. This is all that will happen on my photographic plate or on my holographic recording plate. Between the maxima is kx. So, k delta x, this I have finished. So, theta is equal to 15 degrees, just suppose. Then sin theta is equal to 0.26. Then lambda, suppose I take lambda is equal to 500 nanometer, that means close to, somewhere close to a green light. Then what is your delta x? You just put in all the values, delta x turns out to be 2 micrometer. So, the separation between your two maxima should be 2 micrometer. This part should be 2 micrometer, that tiny. So, the holographic recording plate must be capable of resolving lines that are 2 micrometers apart. Okay. So, that sort of an accuracy you need. So, how can you get that accuracy? You will get that accuracy by very fine grains of silver halide are used. Okay. Very fine grains are used. Then this separation of 2 micrometer can be recorded. You know, it won't smudge into one grain and the other. Suppose the grain is here, this is not smudged onto this or smudged onto that. They should be distinct, this silver halide. Okay. Only if it is distinct, then you are getting a accurate picture of that, of the interference pattern. Very fine. But then plates with high resolving power have low sensitivity and need longer exposure times. Okay, so here is a problem. You have to tread a very fine balancing act you have to do. So, if your grains are very fine, okay, if your grains are very fine, then your resolving power is high. Okay. But if there are such tiny grains, it may not be able to record the light and shadow very well. You are getting a very good resolving power, but your sensitivity becomes low. Such a fine grain, it is not, it's not sensitive enough to the light. That means from silver halide, it may not be changing over to silver. Okay. So, sensitivity and resolving power, they are both are competing factors. Okay. And then you need longer exposure times. Okay. So, if you want a better sensitivity, then you have got the resolving power, say, but you want a better sensitivity. It isn't that sensitive because they are fine grains. Then you need to expose it for a longer time. Okay. So, sometimes high power laser, pulsed lasers are used, where the exposure time is reduced to the pulse width. Okay. That you can understand. So, you just give a pulse of light instead of a continuous wave. Till now we have spoken about wave front which is going through. So, we haven't said anything about pulse or continuous wave. We've imagined it to be continuously there all the time. So, you don't want to expose your silver halide to too much light or too little light. It should be just the right amount. So, that is the exposure time, which is true about in any ordinary photographs also. A photographer doing a serious photography knows what is the exposure time for taking a picture of a certain thing. Okay. So, your final photograph actually depends on that. So, here what you can do is you have a laser and you choose the pulse width in time, okay, to have a control on the exposure time. So, then in that case you will get the resolving power and the exposure and the sensitivity, both will be in your favor. So, this is some of the factors which affect the quality of your holographic recording. Okay. So, there was one Russian scientist who thought of how do I make this holographic plate recording more sensitive and record much more data or have a better resolving power. Okay. Then he thought of making a 3-dimensional holographic plate. 3-dimensional means it's not, it's a thick hologram. Instead of having a thin film like this, your hologram, you have a thick film. So, by thickness, that's what he means by, he meant by a 3-dimensional one. So, till now we kept thinking of one xy plane and one-dimensional structure on which you record all these lines or shape or whatever. It's like a one-dimensional thing. Now you give this a slight thickness. Maybe you can give a thickness like this. Okay. So you give a kind of a thickness. So all your silver halide or the emulsion, the gel and the emulsion is in a thick part like this. Okay, that's why it's called 3-dimensional. So when your reference beam and the signal beam, they are interacting with each other and they come like this, they are actually forming a pattern, whatever pattern it is, partly into the thickness of the hologram. Okay. It's forming a pattern like that into that thickness. So you are recording more. You are some of the data which may not come on, say, just a 2-dimensional part will come onto the thickness part of it. Okay. So there is more data to be recorded, and again you are sort of solving some of the resolving power and the sensitivity problem which I discussed now. So I could have say this is that prism which I was speaking about. I have this prism as before, this is my wavefront, and I also have this wavefront here which is my signal, and the plate and the holographic plate that I have here is like this, and these are all coming at an angle. So the recording on this thick plate will be something like planes like this. Okay, instead of just an undulating pattern which is a one dimension, you have kind of planes which are happening. Okay, so here I just write, in thick holograms the interference pattern of a ray is not 2-dimensional but 3-dimensional and covers the entire thickness of the emulsion. So that emulsion is this thick, and so these beams are propagating partly inside this material and forming these layers. Let k and k0 be the wave vector of the signal wave and the reference wave. Then the square of the amplitude of the field strength can be written as E star E as before, mod E square. So here actually I have written the wave as e to the power I k0 dot r in polar sort of coordinates, because now this 3-dimensional picture comes into view. That's why I have taken polar coordinates like k. K is the wave vector, not either along x or along y, which were those Cartesian coordinates which I have done previously. Here I write the wave as e to the power I k0 dot r plus E1 e to the power I k dot r. So, R is actually that vector, I have just called that vector, and K also, as you know, is a vector, but we were just taking a component of that K along the x direction or along the z direction in the previous derivatives. So, here I take this sort of a wave and take the square of that, as we have done before, to get the transmission. Okay, so, E0 square E1 square to E1 E2 cos K0 minus K dot R. So, here I think I can just show it here. If you see this structure, this is K0 and this is K. Okay. So, one is the reference wave, K be the wave vector of the signal wave and the reference wave, signal and the reference wave. These two, what is the addition of these two? Addition gives this vector. So, here I am doing some vector addition. Okay. So, it is K minus K0, which is this line. Okay. And theta by 2 is this small angle here. It is half the angle between K and K0. Okay. And my R is here. So, this R means at this distance R, I have to record my interference pattern in this 3-dimensional structure. It will give a 3-dimensional structure on its own. Okay. So, just try to imagine what I mean by this 3-dimensional structure. It is just a thick plate and you get another x, y and z directions to your recording on the silver halide or the emulsion. You are getting a 3-dimensional recording. So, here, so K0 minus K dot R is equal to 2 pi m, m is an integer. Okay. The condition for maximum value of E square is of this form. Obviously, you know it from this part. When I open this out, this is what it comes out to be. So, cos of this has to be 1. So, K minus K0 minus K dot R should be 2 pi m. M is an integer, you can just forget about it. The distance d between the planes is K0 minus K d. In place of R, I have written d is equal to 2 pi. D is this. Between the planes means between the planes of the recording, all this, the interference pattern recording, those are the planes that are formed. Okay. Just imagine, those are the planes. Instead of being just lines, now they are planes. So, you have K0 is 2d and K is 2 pi by lambda. So, K0 minus K is 2 pi K sine theta by 2. Theta by 2 comes out to be this. So, it is an angle between the two wave fronts, okay, and 2 this. So, finally, d is equal to lambda by 2 sine theta by 2. See, this thing looks very familiar. You know, it is, you can take it as the equation of a grating. 2d sine theta by 2 is equal to m lambda. Remember, that was the equation of a grating. So, it is like, you know, these have so these are like thin films. Okay. Suppose I just revert this, inverse it, and I am getting an incident beam which is at an angle alpha, which is the same as this alpha. Okay, this is the incident beam. And then you are getting reflections from each surface. You are getting these reflections and you know these these follow the equation of a grating, or they can be called as Bragg reflections. From solid state physics, if you remember Bragg's law, there also you have the layers in your material and your incident light gets Bragg diffracted. So this equation is very much like that. Okay. Or you can think of it as layers of thin films, and then these are interfering with each other to give you the final wave front or the final pattern. So I can think of these layers. These layers are these layers, and this incident light is the reconstructing wave. So it's the reconstructing wave, and it is going through these layers, and it is experiencing Bragg refraction because of those layers. So in my emulsion, I have made, instead of lines, I have made layers, and it follows this kind of an equation. And here again you can see, you know, the light that can be used for reconstruction can be white light. Okay? It can be white light. That means it need not be a monochromatic light. It can have so many wavelengths, lambda 1, lambda 2, lambda 3, basically white light. And still you will get the reconstruction of your object into an image. Why? Because see, only those lambdas will be taken into consideration which satisfies this condition. So you can have any of these lambda, it will just pick up one of those, and those will be refracted back or reflected back, and those will have constructive interference. So you really, your input light need not be monochromatic at all. When you are constructing it, of course, monochromaticity and all that has to be looked into, but here it does not matter, and you will still get an image. So this is how a hologram works. So the basic idea of hologram is, scientifically, if you look at it, of course it has this aesthetic part to it. It gives you a 3-dimensional image, and it is used in the industry as that. But then, as I have said in my first few lectures, the part is you get these holograms on many of your credit cards, debit cards, and many other places. So it's like information that is coded onto this hologram, and it cannot be copied easily. So the fraud part becomes a bit less in case you have a hologram. Okay. So that is a serious part of it, and the aesthetic part is, of course, it's a 3-dimensional case. And another serious part is you are encoding a lot of information in this hologram, which you have to retrieve in your own way. I hope you have got a good idea of what holograms should be, or good idea of holography. So this is my this is the last lecture in the series of light amplification, intensive course on lasers. And as you know, I have just give you a brief idea of what I have gone through or what I have tried to convey to you. So this course conveyed the working of a laser. Okay. You have got the concept of laser. So, if using that concept you can build lasers, and then you have got certain uses of lasers which are used in so many widespread fields. Okay. So, some of those uses I have given you, and the very prominent ones are laser Raman spectroscopy and in spectroscopy in general, scientifically. Okay. Other than that, in medicine I have given you the uses. Okay. So, a good understanding of lasers, even if you, I would prefer if some of you would get into the field of lasers to make lasers, it would be great. But even other than that, even if you are a user of laser, this sort of a knowledge will definitely help you. So, good luck to you.